Hello everyone and welcome back to the Math Econ. If you are preparing for ISI MSQE Economics entrances or simply want to strengthen your understanding of mathematical economics, then today's video is for you. Today we are going to solve two very interesting questions from the ISI MSQE 2025 PEA examination based on one of the most important topics in growth theory, the Solow Growth Model. These questions may look simple at first glance, but they test whether you truly understand the intuition behind steady states, capital accumulation, and the golden rule of growth. So don't just focus on getting the answer, try to understand the logic, because once the concept becomes clear, similar questions can be solved in a matter of seconds during the examination. Grab your notebook, pause the video whenever necessary, and let's begin.
We are given a standard Solow economy with the aggregate production function y equals the square root of k times n, where y is output, k is capital stock, and n is the number of workers. The question also tells us that g equals 0, which means no technological progress, and n equals 0, which means no population growth. The savings rate is S and the depreciation rate is delta. We need to find the steady state capital per worker and steady state output per worker. So let's understand what's really happening here. Imagine a village called Solow Land, where the only business is making toys. To keep things super simple, the villagers only have two things to work with: the kids in the village, who are our workers, and the machines they use. So the total number of toys they can make depends on both how many kids are working and how many machines they have. We define machines per worker as the total capital divided by the number of workers, and output per worker as the total output divided by the number of workers. Looking at things this way makes the whole economic puzzle much easier to solve. Simplify that production function. We start with y equal to the square root of k times n. If we divide both sides by the number of workers, n, we get output per worker y equals the square root of k over n, which simplifies to the square root of k. This gives us the per worker production function y equals f of k equals the square root of k. As we were saying, each year the workers put a part of their income, at a saving rate denoted by S, into a kind of piggy bank. That saved output is then used to build new machines, so more saving directly translates into more machines. Now, just as saving builds things up, there's the other side of the coin, depreciation. Every year, some machines wear out or break, at a rate we call delta. So the higher that depreciation rate, the more machines you lose, which brings us inevitably toward a balance between machines being built and machines breaking down. So let's connect all these ideas to our model. We know that our per worker production function is f of k equals the square root of k. At a steady state, the number of new machines being built exactly balances out the number of machines breaking down, giving us the fundamental equation s times the square root of k equals delta times k. So, let's apply this to our model. Plugging that production function into the steady state condition gives us s times the square root of k equals delta times k. To find the steady state capital per worker, we divide both sides by the square root of k, which leaves us with s equals delta times the square root of k, and then we square both sides to get k equals s squared over delta squared. Now that we've nailed down the steady state capital per worker, let's find the steady state output per worker. Since we know that output per worker y equals the square root of capital per worker k, we can just plug in our steady state value for k. This gives us the square root of s squared over delta squared, which simplifies beautifully to s over delta. Now that we've found our steady state values, it's time for the final showdown. Looking at the options, option A, B, and C don't match our results, so we have to go with the winning choice, D, none of the above. To solve this kind of problem, the golden rules are always to first convert into per worker terms, then find the per worker production function, apply the steady state condition, solve for the steady state capital per worker, and finally calculate the steady state output. Alright, let's dive into question 2, which is a direct continuation of our journey in Solow Land. Now we're assuming that the depreciation rate denoted by delta is 0.1. This question asks us to find the steady state consumption per worker and the special saving rate that maximizes that consumption, famously known as the golden rule saving rate. To tackle this next challenge, we first need to recall what we found in question 1. We have the steady state capital per worker k star equals s squared over delta squared, and the steady state output per worker y star equals s over delta. Now let's dive into the concept of consumption. Workers produce output, and that output can either be consumed or saved. So, if consumption is what's left over after we do our saving, the math works out beautifully. As you can see, consumption per worker C is equal to 1 minus the saving rate S times total output per worker Y. So, to find the steady-state consumption, we substitute the value of Y star from question 1, which was S over delta, into our consumption equation. This means the steady-state consumption C star is equal to 1 minus the saving rate S, all multiplied by S over delta. Now that we have our steady-state consumption formula, our goal is to find the specific saving rate that makes that consumption as high as possible. Since delta is a constant, we just need to maximize the term S times 1 minus S. By taking the derivative and setting it to 0, we find that the optimal saving rate is exactly 0.5. Now that we've found our candidate, we need to be absolutely sure it maximizes consumption. We do this by checking the second derivative, which is equal to -2. Because this value is negative, we've officially confirmed that this is a maximum, proving that a saving rate of 0.5 is indeed the golden rule saving rate. We found our value, so it's time to check the options. Our findings show the steady-state consumption per worker is S times 1 minus S, all divided by delta, and the golden rule saving rate is exactly 0.5. Comparing this with the choices, option A matches our results perfectly. We started with the output per worker from question 1, defined consumption as output minus savings, substituted the output into that equation, and then maximized the result to find that the golden rule saving rate is exactly 0.5. If you enjoyed this deep dive into the Solow Growth Model and found it helpful, please give this video a thumbs up, share it with your friends, and don't forget to subscribe to the channel for more economics tutorials. Thanks again for watching, and until next time, keep exploring the fascinating world of economics.